Hello, ma'am. Sir, I am Dhruv Agarwal. I am a fourth year student from Electronics and Computers branch.
I'm Alok Ohri. I'm a fourth year student from Electronics and Computer branch.
I am Ekroop Kaur. I am fourth year student from Electronics and Computer branch.
I'm Arpita Sharma and I'm fourth year student from Electronics and Communications branch.
I'm Dhruv Khullar. I'm a fourth year student from Electronics and Computers branch.
We, the students from group number 52, are here to present the final capstone project submission on the topic Low Power and Low Area Test Data Compression for SoC. We have completed this project under the guidance of Dr. Harpreet Vohra and Dr. Gaganpreet Kaur from ECED department. Introduction. In today's era, small size of electronic gadgets is preferred. Therefore, small chip applications have become reliable and cheaper with latest technologies in VLSI industry. Achieving high test quality in reduced VLSI geometry increases the complexity of testing methods because of huge volume of test data. Automatic testing equipment is used during the testing of the chip, which undoubtedly reduces testing efforts but has limited memory in comparison with the huge volume of the test data. So we propose test data compression to reduce the burden on ATE. Project overview. We propose increasing the compression ratio of existing algorithms by compressing data through the use of statistical and run length encoding. We reduce the switching frequency of data, which reduces the power dissipation. This encoded data is decoded by a decompressor circuit designed in HDL. The proposed design is also verified against VLSI benchmark test vectors and are implemented on FPGA. This is achieved by Hamming distance 9C compression technique followed by hybrid filling. It provides a low area overhead in comparison to the previous approaches and benchmark circuits. In the upcoming slides, we'll be discussing Hamming distance 9C compression technique hybrid filling in more detail.
From straightforward code-based techniques to combine or hybrid methods, following are the various methods used for the lossless compression. Hamming distance. Hamming distance is the distance between the two test vectors equal to the number of corresponding mismatched bits, which is the protrusion of don't care bits. Here, two-dimensional rows and column test vectors, reordering and power optimization don't care bit filling method is applied. The WTM, that is weighted transition matrix, is used to estimate the power consumption due to the scan test vectors. Then comes the 9C compression, which is dictionary-based working on fixed-length blocks of input test data. The test vectors are partitioned into group of k bits, and encoding is performed on each k bit block. With this method, we try to achieve the compression code with exactly 9 code words. Besides 9C, another method of low-power hybrid filling is used that replaces the don't care bits in an initial test data with either 0 or 1 based on some algorithm or pattern of previous or following bit string. It has three major steps such as don't care bit position identification, counting, and filling. The former decides the position of don't care bit and later decides the don't care bit value. The flowchart for hybrid filling is described in the figure shown.
Firstly, we did simple data preprocessing and converted the input test vectors into a single Python list. Next is the code for Hamming distance. In this, we implemented list compression and took the block size as 14 for this particular test bench. This is the obtained list. And further, we combined this list into a single list. Following which is the code for 9C compression, where we divided the blocks into two equal halves and assigned unique value based on the count of number of zeros and 1 respectively, and later mapped those values to 9 different cases. These are the 9 different cases. And finally, we programmed HybridX filling for replacing all the remaining don't care bits from the previous output. And this is the compression ratio which is achieved.
This is the decompressor architecture for 9C compression. Here we are using a FSM to get the output at every combination of input. This is the Verilog code for the decompressor architecture. It is based on an FSM. As you can see here, I have simulated the Verilog code. Here, when the reset goes to 1, the decoder starts working. For an input starting from 0, the output becomes 8 times 0. For an input starting from 1 1 0 0 0, the output becomes 4 times 0 and 4 times 1. Here, this change in output happens after 3 clock cycles as the FSM checks at every input bit. As you can see here, for an input starting from 4 ones, the output switch stream becomes the unique code which comes after 4 times 1, and this happens after 9 clock cycles. We have implemented the Verilog code on an FPGA board. This is a Z board. Here the switches are inputs and the LEDs are outputs. As you can see, when the switches are all low, the output becomes 0, 0, 0, 0, 0. And when the input is 0, 1, the output becomes all ones. As you can see, as we keep changing the input, the output also keeps changing corresponding to the input. Here, as you can see, the combination is 1, 1, 1, 0, 1. So the output is 4 times 0 and a unique code after the input.
The compression ratios for different test vectors which have been obtained. This figure shows the graphs for different K values, and below that is schematic for decompressor architecture.
To conclude, it can be said that the gist of the given project resides in the fact that deals with data compression using efficient algorithms with different types of compressors and decompressors, minimizing the overall power consumption, thereby reducing the memory size and minimizing the overall cost, which was our point of interest in the beginning of the project. From using straightforward code-based techniques to combining the hybrid methods, this project provides a total overview of the various methods used for lossless compression of the input side test data to achieve the goal of minimum power dissipation and dwindling the area overhead. Thank you.